Thank you for the introduction, and I want to start by saying thank you to the organizer for letting me give a talk in this conference. I will be speaking about the classification problem for codimension 2 polar homogeneous foliations on symmetric space of non-compact type, and the main idea is to see how the interplay between these spaces and real semi-simple algebras allows us to attack this problem from a purely algebraic approach. So let's start by giving the definition of polar action. So assume that we have a complete manifold M, which we always assume to be Riemannian, and there is a connected Lie group G, which acts properly and isometrically. This in practice is the same as considering closed subgroups of the isometry group. We will say that the action is polar if there exists a complete submanifold sigma that meets every orbit perpendicularly. These submanifolds are known as sections, and in the case that they're flat, we say that the action is hyperpolar. So for example, here on the right, if I can get the pointer to work, so here on the right we have the main example of a polar action, which is the group of rotations SO2 acting on the plane, and every straight line that goes through the origin is going to constitute a section. Also from the picture we can already see the two main properties of sigma. The first one being that the dimension of any section is going to be equal to the minimum codimension of the orbits. This is known as the homogeneity of the action. And secondly, sigma is always a totally geodesic submanifold of the ambient space. So before we go any further, I just want to share some more pictures of how polar actions look like on the Euclidean free space. So for example, on the upper left corner, we have the action of R2 by translations. We have also the action of SO3 giving rise to spheres around the origin. The action of SO2 times R, which gives rise to cylinders as principal orbits. And they're centered around the C-axis, which is a singular orbit. Or the action of SO2. Or the action of SO2 by rotations around the Z-axis, in which the singular orbits are points and the principal orbits are circles. Now it's a little hard because I have one remote for moving. So yeah, I think I'll change this. Again, note how the sections are only straight lines and planes. The fact that they are totally geodesic means that in the Euclidean space, the only possible candidates for a section are going to be affine subspace. But at any rate, the main problem that one would like to approach is that given an ambient manifold M, we would like to classify all polar actions on M up to orbit equivalence. So by orbit equivalence, I mean that if we have two groups acting polarly, we say that their actions are equivalent if there exists an isometry of the ambient space, the orbits of the first group to the orbits of the second group. So if we want to have some degree of success when dealing with this problem, we first have to work with manifolds which have a large enough isometry group so that there are non-trivial isometric actions. And since we need to know, since sections are totally geodesic, we will need to know some properties about their totally geodesic submanifolds. So in our case, we decided to link toward non-compact symmetric spaces, and we will focus on polar homogeneous foliations of codimension 2. So we'll be working with polar actions that have no singular orbits and whose section is going to be a totally geodesic surface. Okay, so let's give some algebraic preliminaries that we need in order to understand the main theorem. Assume that M is a symmetric space of non-compact type, then we can write M as the quotient G mod K, where G is the connected component of the isometry group containing the identity, and K is the isotropy at a fixed point O. Now, the fact that M is symmetric means that at every point we have a geodesic reflection, and the geodesic reflection at the origin induces a Lie algebra involution known as the Cartan involution. This in turn induces an eigenspace decomposition of the isometry algebra G as K, which is going to be the eigenspace of 1, and is also the isotropy algebra, and P, which is the eigenspace of -1, and not necessarily a subalgebra, but it's a subspace that may be identified canonically with the tangent space at the origin. So the fact that M is non-compact means algebraically that if we consider the Killing form of the isometry algebra and we restrict it to P, this gives us an inner product. So we extend it on one hand to the whole isometry algebra by the formula given here, taking x and y to minus the Killing form on x and theta y, and on the other hand we extend it to the whole ambient manifold by assuming that our metric is left invariant. So from now on, we will always assume this this metric is the one given in our space. In the case that M is irreducible, this is not a problem, and in the reducible case, this means that we will have to make some dilations on each the round factor of our space. And as I said earlier, we need to have some properties about totally geodesic submanifolds, and they are characterized in this setting algebraically by means of Lie-triple systems, in the sense that given a vector subspace V is the tangent space to a totally geodesic submanifold at the origin, if and only if it's closed under the triple bracket operation given here. So these are known as Lie-triple systems. And this correspondence restricts to a one-to-one correspondence between flat totally geodesic submanifolds and abelian subspaces of P. Okay, so apart from the Cartan decomposition, the other main tool that we will need is the root space and Iwasta decomposition for the isometry algebra, which is defined as follows. So take a maximal abelian subspace A in P. One can easily check that the adjoint image of A consists of symmetric operators that commute. So in particular, they are all diagonalizable in a common basis. So we can write G as the direct sum of its common eigenspaces. So to be more precise, we define G alpha to be the set of all X that are eigenvectors for the adjoint image of H with eigenvalue alpha of H for every H in the maximal abelian subspace. These are called root spaces when they are non-zero, and in that case we say that alpha is a root. So we get this root space decomposition where G can be written as the sum of G0 plus a finite direct sum of root spaces associated to a finite set of roots called sigma. This set can be given an ordering, so we can talk about positive roots, and among the positive roots we can also consider those that cannot be further decomposed as a sum of positive roots, and these are called simple roots. And from this construction we get the Iwasta decomposition defined as follows. Take all of the root spaces corresponding to positive roots and you sum them up, and this creates a nilpotent subalgebra called N, and we get that G is the vector space direct sum of K, A, and M, where N is nilpotent, A is abelian, K is compact, and A plus N is solvable. And there are analogous decompositions for the isometry group by considering the corresponding connected subgroups for K, A, and M. So, if you're not familiar with the theory of real semi-simple algebras, the first instinct would be to think that the roots behave exactly the same as the ones in complex semi-simple algebras. But there's a small caveat here that is going to make all the difference. In the complex case, there is this Cartan subalgebra that plays the same role as our A given here, and in the complex case, A is equal to G0. In the real case, what happens is that G0 is equal to a part in K, which we call K0, and a part in P, which coincides with A. And when K0 is not 0, this gives us some problems when trying to do this classification. So for the purposes of this talk, we will assume that the vector subspace K0 is the zero space. This gives rise to the notion of split semi-simple algebras in the sense that the isometry algebra will be said to be split if we have precisely what we want, that K0 is 0, or equivalently that G0 is A. So note that G0 is the centralizer of A in G, and in particular we see this third condition that says that being self-normalizing will be equivalent to being self-centralizing for the case of this maximal abelian subspace. Now, this is not like the condition is going to give us the empty set of symmetric spaces. It turns out that for every complex semi-simple algebra, there is a unique split real form, and to this split real form corresponds a noncompact symmetric space. So for example, we have all of the symmetric spaces here that come from considering the corresponding complex simple algebras of classical type. And we solve the problem for these spaces. Okay. At any rate, we're trying to work in the algebraic terms, so we need to have an algebraic characterization of polarity, and it's given in the following criterion. So let us assume that we have a subgroup H that is closed and connected, and suppose that we already know that it induces a homogeneous foliation on our symmetric space. So we can consider this normal space HP paired, which is the orthogonal complement. This O minus here denotes orthogonal complement. So we take the orthogonal complement of the projection of H in P inside of the tangent space P. If you think about it for a bit, this is the same as taking the orbit of H to the origin, and this space is going to be the normal space to the corresponding orbit at O. Since we're working with foliations, this is precisely the only possible candidate for a section on our action. So the algebraic characterization gives us the following. The action of H is going to be polar if and only if HP perp is a Lie triple system, so that is if it generates a totally GLSX submanifold and the bracket of HP perp with itself remains orthogonal to H. This condition essentially means that this orthogonality remains true among geodesics. And as a direct consequence, we deduce that the action is hyperpolar if and only if HP perp is an abelian subspace of P. So
what is hyperpolar again?
What?
In hyperpolar?
Yeah, so we have this section of our polar action. Hyperpolar means that it is flat. So in our case, it would be a Euclidean space. Okay. So with this in mind, we are now ready to understand how the classification works in low homogeneity. So,
how restrictive is that condition that H defines the foliation? Is it easy to check or?
Is it easy to check? So what we will see later is that all examples come from considering the solvable part of the Iwasta decomposition, and they all induce foliations. So in that case, checking that it's a foliation is trivial. So the problem is that if we want to go to in a more general setting, we only know that this algebra that induced foliations is solvable. So we have to keep that in mind. So it's not as easy as in this case. Okay. So let's start by commenting briefly on the case of codimension 1 foliations. It's very easy to show that every community 1 action is hyperpolar. So classifying community 1 polar foliations is just classifying community 1 foliations. This was done firstly by Bernd and Tamaru for irreducible symmetric spaces of noncompact type, and subsequent works were done in order to extend their classification to general symmetric spaces of noncompact type. And the idea to construct this is to take the solvable part, A plus n, and to remove, to take the orthogonal complement in this subalgebra of a normal vector chosen in a coherent manner. This gives us two possible families. The family of foliations of Horst spherical type, which comes from taking the orthogonal complement of a vector in the abelian part. For example, we have here the Horst sphere foliation in the hyperbolic plane, which comes from considering this. And we have this second family, which is called the solvable type, which now comes from removing a straight line from the nilpotent part, as long as the straight line is contained in a simple root space. And again, here we have the example in the hyperbolic plane. So in this case, this is totally solved. We know that all community 1 foliations are equivalent to exactly one of the types given here. Now, this procedure that is given to produce all community 1 foliations can be generalized to a general procedure to construct hyperpolar homogeneous foliations in arbitrary codimension. This was done by Bernd, Diaz Ramos, and Tamaru, and for illustration purposes, we're going to see this construction in codimension 2. So there are essentially 3 ways to construct these hyperpolar homogeneous foliations. We can either take 2 normal vectors from the abelian part with no restriction. We can take 1 vector from the abelian part and 1 vector from the nilpotent part, as long as the vector here belongs to a simple root space and the corresponding vector in the abelian part is orthogonal to the simple root that appears here. Or we could take both vectors from the nilpotent part as long as they are in root spaces associated to orthogonal simple roots. So in this case, it has been proven that every hyperpolar homogeneous foliation is equivalent to at least one of the ones that appear here, but the matter of orbit equivalence is still not solved. So at any rate, in the case of codimension 2, either the action is hyperpolar, which is the case studied here, or it is not hyperpolar. So in this setting, this section is now going to be homothetic to a hyperbolic plane, and this was the case that we wanted to approach ourselves. So the general strategy that we followed will be given here for the case that the isometry algebra is split, and it goes as follows. The first step was to note that if we have a closed subgroup inducing a homogeneous foliation of codimension 2, then the isometry, the corresponding Lie subalgebra H, can be assumed to be solvable. In particular, it must be contained in a maximal solvable subalgebra. So these are known as Borel subalgebras, and they have been studied by Mostaf. So We go to a result from most of on maximal solvable subalgebras, and we can deduce that up to orbit equivalence, H is contained in the direct sum of K0, A, and N. But since we are assuming that we are split, we know that K0 is 0, so we get that we are in A plus N. And we go back to your question, Ramiro, that now we have the main advantage that from this we obtain that every subalgebra of A plus N corresponds to a closed subgroup, which induces a foliation. So in this setting, we have reduced the original problem to determining all codimension 2 subalgebras of the solvable part which satisfy the algebraic characterizations given here. So now the problem is to determine the H's in this manner. So suppose that we have such a subalgebra of codimension 2. What we first did is to consider this extension of H to H tilde by adding all of the positive root spaces that do not correspond to simple roots. So we're working on level higher than 1. It's very easy to check that this is a subalgebra, so it must be either the whole A plus N, it could have codimension 1, or it could be H again. This first case of being A plus N can be discarded quite quickly, and to discard the case of codimension 1, we resort to Bernd and Tamaru's article on codimension 1 foliations, where they, in particular, give the structure of codimension 1 subalgebras of AN. We use this paper, and we deduce that, in reality, this subalgebra must be exactly H, so in particular, all of these root spaces are already in our subalgebra. And therefore, the normal space must be obtained by projecting vectors in the abelian part and in the simple root spaces. So this is a much smaller subspace, and now we can make explicit computations here in order to determine all of the non-abelian Lie triple systems in HP perp of dimension 2, which corresponds to these hyperbolic planes. And we obtain from this that the orthogonal complement of H in the solvable subalgebra is spanned by 2 vectors. One vector is going to be in a simple root space G alpha, and the other vector is this vector H alpha in the abelian part, and it's characterized by this formula. So it's simply the dual vector to the simple root alpha. So because of this, the original subalgebra is simply going to be the orthogonal complement of H alpha and of psi, but in particular root spaces are one-dimensional in this setting, so it's the orthogonal complement of all of G alpha. So what we got here can be summarized in the following theorem, which asserts that given a codimension 2 polar homogeneous foliation on M, assuming that the isometry algebra is split, either the action is hyperpolar, which was already studied, or it is not hyperpolar, in which case it's orbit equivalent to the action induced by the subgroup whose Lie algebra is precisely the kernel of alpha, where alpha is a simple root, plus the orthogonal complement of the simple root space G alpha in M. So this would finish the classification in codimension 2. So this is what we have already solved, but we are now trying to extend this classification into the general setting by not assuming that K0 is 0, and it's worth noting that more examples appear in this case. So for example, one may remove an abelian subspace from a simple root space, and this gives a new example of foliations. And we know that they are not orbit equivalent to these examples, because one can easily check that here this section is going to be a hyperbolic plane of sectional curvature -1, where in this new setting, the sectional curvature of this section is going to be depending on the length of the root that we consider. But at any rate, this was everything that I wanted to talk to you about.